Hello everybody, welcome back. Hope you're all excited. We're finally at the end of the Csmc 2013 paper. That's Canadian Senior paper from the year 2013. And as I said, we're at the very end. We are at the end. We've made it. We're at question number 3 in B part. So it's written portion. I expect this to be the long one. The last question is usually the hardest. But enough speculation. How about we jump right in and take a look at the question. Alright, so question number 3 here. If m and n are positive integers, an mn sequence is defined to be an infinite sequence, x1, x2, x3, of a's and b's, so that if x1, so if the ith number in our sequence, or if the ith letter in our sequence is a, then xi plus m is b. So m positions after an a will have to have a b, and this says that if you have a B, then n positions later you have to have an A. For example, AB, 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 AB is a 1-1 sequence because one space after an A we have a B. One space after a B we find ourselves with an A, and so on and so on. Alright, so A part. Determine all 2-2 sequences. So 2 spaces after an A, we'll have to have a B. And 2 spaces after any B, we have to have an A. So we have 2 possible ways any sequence could start. We could have an A or a B. So we start with an A, then after 2 spaces we have to have a B. So I don't know what this is, but I know this has to be a B. And after two spaces after any B, I have to have an A. Okay. So this is looking fine. 2 spaces after every A, I've got a B. So we have this blank spot right here. Suppose it's an A. Now, if we put an A in there and that tells us that, this has to be a B for some reason, we know that this can't be a 2-2 sequence because it would sort of conflict with itself. So if we put an A there, that tells us this has to be a B. So this has to be an A, and this has to be a B, and this has to be an A, and so on. So we get one sequence. What about it if it were a B? Okay, we'd have AABB, AABB, AABB. What if we had a B in this second spot? All right, we put a B in here. Well, then we get 2 spaces after every B, we have to have an A. 2 spaces after every A, we have to have a B, and so on. I know they're not going to conflict later on, and perhaps I should write that, but I don't think I will. I know they're not going to conflict later on because our first number determined every odd position, and this is determining every even position because 2 spaces after the B, we have to have an A, so that's going to be even, and then even. It's never going to say, our first sequence, our odd sequence, is never going to come into conflict with the numbers in the even positions. So that's 2 sequences. How about if we start with B? We get B, I don't know, but then there has to be an A, 2 spaces after the B. Then 2 spaces after the A, there's got to be a B, and so on. So we have 2 choices here, and those give us the sequences BA, A, B, B, A, B, B, A. And we could have B, B, A, B, B, A. These are all 4 of these are distinct. I mean, these 2 are clearly distinct, and they're going to be distinct from the ones on the previous page, because the ones on the previous page both started with A. So we get 4 sequences. I have no idea what word I was trying to write there. Right? If we felt inclined, we might give a little bit more explanation as to how we know these are going to be okay in the, further down the line. But I would say at this point it's clear. They're just trying to give us, the first questions usually just give us a handle on the new concept that they introduce. So there's all the 2-2 sequences. We have all 4 of them. And that concludes A part. B part, show that there are no 1-2 sequences. Okay. So let's suppose there were a 1-2 sequence. What would that look like? What could it start with? If it starts with an A, then right after it, 1 position after every A, we have to have a B. And then 2 positions later, we have to have an A, and so forth. So let's try. We get A, and then we have to have a B, and then I don't know what, but then we get another A, and then a B, I don't know what, then an A, and then a B. So this is, we don't know what this is, we could fill it in with 2 possibilities, A or B. If this is an A, we get A, B, A, B, but this should be a B. So we have a problem here. Putting an A here tells me that this A should be a B. Right? This contradicts what we said. We supposed we had a sequence. So if it starts with A, we get this little gap here. If we put an A there, we have a problem. This should be a B, not an A. So let's try a B instead. A, B, B. A, B. Well, this B tells me after every 2 spaces after every B, we should get an A. This should be an A. Contradiction. The sequence is trying to have 2 different letters in the same position. So that's what happens when we start with an A. Either way, we'll get this little blank space, and we can't fill him properly. So we cannot get a sequence that starts with A. Well, how about a sequence that starts with B? All right, we get a B, and then 2 spaces later we get an A. And then after every A, we have to have a B, and then 2 spaces later we have an A. So we get AB space, AB space. So we don't know what this is. So right now to us, this could be an A or a B, this blank spot here. Try A. Well, then we have BA. So the B tells us this B says we should have an A here. I mean, that's how we completed our sequence. But putting an A here says that this A should actually be a B. Well, let's try a B in that spot. All right, let's highlight that that's the empty spot. Okay, well, this B says there should be an A here. And after every A, we have a B. But this B, here, the one we just filled in, says that this second B over here should be an A. And we're at a little therefore statement explaining how we know from these examples that there's no 1-2 sequence. We tried to construct one, and everything has to start with an A or a B, but if we start with an A, we get a gap and we can fill that with an A or a B. Neither one works. If we start with a B, we get a gap in the second number. We can fill that with an A or a B, but neither way works. The rules eventually contradict each other at some point down the line. And so no sequence can exist. And they contradict each other pretty quickly. I wonder if there's a reason for that. We didn't see it 7 spaces down the way. We saw it 2 and 3 spaces down the way. But the point is, no 1-2 sequence can exist. We've shown by exhaustive case checking that this doesn't work, that we can't have a 1-2 sequence. So that's sufficient for B part. Okay, we've explained everything, we wrote it down. C part. For every positive integer r, show that if there exists an mn sequence, then there exists an rn sequence. Okay, so if there exists a 1-2 sequence, then we could have a 3-6 sequence. If there exists a 4-7 sequence, then we could have a 16-28 sequence. That's what it's trying to tell us. Okay. So how best to go about this? Well, we have an example already. We were told at the start of the question that AB, AB, AB is a 1-1 sequence. And we have 4 different 2-2 sequences that we got in part A. We got all 4 of the possible 2-2 sequences. So maybe if we go back and look at those, we could get a bit of a template for how might we get an RN sequence out of an MN sequence. Okay. So the one thing I notice is that we have a lot of AABBs, AABBs going on. AABB, 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 AABB. And I already said that the reason we don't need to check these guys in the infinite case is because this ABABA at the start, it's only going to hit the odd numbers. And this sort of this even sequence, ABABA, it's always going to be on the even numbers. And you'll never have a number that's both even and odd. So you'll never have an A saying, well, there should be a B over here, but a B also saying, well, in that same spot there should be an A. So I think we can just sort of lay copies of the MN sequence next to each other. So if we take our copies of an MN sequence, and we know that at least one exists, and we sort of space them out, we should be able to get an RMN sequence. But if we think that, we need to show it. All right, we know an MN sequence exists. That's sort of our hypothesis. We're assuming one exists. And we want to show that there's an RN sequence. And I'm saying that if you were to take this sequence and sort of spread it out so that we had X1 and then R spaces later we had an X2 and then R spaces later we had X3, we could get ourselves an RN sequence. So instead of X's, we'll use Y's. So we'll pick an index I, and we'll just say for all integers I. And then we'll pick J less than or equal to R. So we'll let I be 1. And we'll let, still J be 1 to R. Let Y R times I minus 1 plus J equal to Xi. Now, if you can't easily parse what I'm trying to do from this sort of index notation, I will write out my example in just a moment. All right, we can see that R times something is going to give us something, a multiple of R. And this J going from 1 to R fills in the rest of all the spaces. J is basically the remainder when we divide by 0. I should really go back while I'm explaining this. Sorry about that. So for any value, if we wanted to find yk for any value, what we would do is we would figure out its remainder when you divide by R. And that could be 1, 2, 3, 4. It could be 0 as well. and we would pick j. J is the remainder. Now, if the remainder was 0, we pick j as r. Okay? And then y is going to look like some multiple of r plus that remainder. Okay? Now, we fudge it a little bit because our sequence has to start at 1. So j can't be 0. We can't have j as 0. That would make no sense. And so that's why we have the I minus 1. And we have j goes from 1 to r rather than the usual remainder, which goes from 0 to r minus 1. Okay? But this really does give every possible k value. If you are in doubt, work out some examples. Okay? Start with a 1-1 sequence and construct a 3-3 sequence using exactly that formula for the new sequence. So all this we have done, all the notation we have sort of fiddled around with, just so that we can properly define a sequence that looks like r copies of x1 followed by r copies of x2 followed by r copies of x3 So we claim this sequence is an RMRN sequence. But we can't just say, oh, we're pretty sure that's an RMRN sequence. We need to actually show why. Well, we need to prove that. So we need to show that the two conditions of being an RMRN sequence are satisfied. So suppose that yi is A. Well, then RM spaces later, we should get a B. This will be equal to xj. It's the best way to write this. This will be I we can decompose into r times, we can't use I again, let's say a minus 1 plus b, with 1 less than or equal to b less than or equal to r, and 1 less than or equal to a. So by definition, yi is going to be equal to xa. Okay. So we want to show that yr plus m is equal to b. Well, we want to know what value, it's some xi or it's some xj. We just need to figure out what that is. If we know what I is, then I plus rm is going to be r a minus 1 plus b. And the b really isn't going to make a whole lot of a difference. Plus b plus rm. We can rearrange that to r a plus m minus 1 plus b. So by the definition of our sequence, we decompose this YIR plus MN, we decompose its index, and then we're able to figure out what X index it corresponds to, what index in the MN sequence we have it corresponds to. Well, it corresponds to XA plus M. And since XA was an A, XA plus M has to be a B because this was an MN sequence. So we've shown one condition. Now let's suppose XI was a B. Well, by the exact same work, we can show that YI had to be XA, so XA is a B. All right, we've done the exact same work we did over here. We skipped writing out a little bit of the steps. We used the same A from over here. But if YI is a B, well, it has to correspond to some X index because it's one of our copies of XA. So XA's got to be a B because YI was a B. And what happens after n spaces after any B? You get an A. So XAN is an A. Well, wouldn't you know it, the one that we're looking for, we want our n spaces after YI to be an A. And that's exactly what we get. So we get ourselves that if you have at least one MN sequence, then you can get an RM-RN sequence. Now, I bet that there are more ways to do this. If we had two different sequences, X1, X2, X3, X4, and Z1, Z2, Z3, Z4, we could probably mix and match. We could probably go X1, Z1, Z1, X1, X2, Z2, Z2, X2, that sort of stuff. We could sort of layer them in because they're not going to interfere with each other. But that's just idle speculation. The important thing is we have solved this question. We have proven that we can get an RM-RN sequence. So we do have C-part done. And if any stray thoughts like that pop into our head, we keep them in the back of our head. And if they're useful in later problems, we can develop them. If not, it's something for us to work on after the contest. All right, D part. So the last part, the final part in the whole contest, determine all pairs MN for which there is an MN sequence. Okay, so we don't have a whole lot to go on. We have two examples of where there are sequences, 1, 1, and 2, 2. And we have one example where there are no sequences. But we know that if we get a sequence, then all multiples of those sequences are fine. Okay. So, with something like this, just because of the way we've had to deal with this question, just thinking about the structure of the question for a moment. We're introduced to the 1, 1 sequence. Then we're asked to find all the 2, 2 sequences. Now this, it gives us a little bit of information on, it sort of gets us ready for dealing with these things. It makes sure we understand the definition of an MN sequence by finding all of these ones. But it also informs our question C. 2, 2 is, well, just 2 times 1, 2 times 1. So it's an example of going from an MN sequence to an RM-RN sequence. So the 2, 2 sequences not only serve to introduce us to the topic, but they also form an example we can use to create the bigger theory later on in C part. So, because M and N can wildly vary, we have no bounds on these guys. My first instinct is to try and develop other general ideas of when MN sequences can exist. So we know that if you have an MN sequence, we can get an RM-RN sequence. Well, what if we have an RM-RN sequence? Can we get an MN sequence? Okay? Because then what we could do is we could say, okay, the MN sequence, we can reduce it to talking about exactly when M and N have a greatest common divisor of 1. Okay? Another thing we might want to do is these 1-2 sequences not existing. What about 2-1 sequences? Should be the exact same thing. So if you have an MN sequence, can you get an NM sequence? So those are two thoughts that pop into my head. And since we don't have a clear plan of attack, the best thing to do is experiment. If we're wrong, if it's not going to lead anywhere, at least we have part marks that show we were thinking about the problem and doing work. So we get two sort of theory-based questions. Okay, so those are two questions that might give us a broader understanding. Okay. So, just thinking about it for a second, I was thinking about it while I was writing that down, and I think I have ways to do both of them. So if we have an MN sequence, after every A there has to M steps after every A there's got to be a B, and N steps after every B there's got to be an A. So these X1s, X2s, X3, these are going to be A's and B's. So let's define a new sequence, and it's going to be an NM sequence. So it's an A if xi was a b. We're just going to sort of swap the values. If we had an A in this sequence, then we're going to have a B in this sequence. A, B, B's, A's, they're going to sort of swap. And that way, we should get an NM sequence. So if yi was a b, we're actually now showing that this is going to be an nm sequence. So if we have yi as an a, n steps later we should have a b. Well, we can prove that. If we have yi is equal to a b, then xi is equal to a. And since the x's was an mn sequence, we know that m steps later we should have a b. M steps later we should have a b, but yim is the opposite of that. So we've created an NM sequence from an MN sequence. Now I'm going to drop the word sequence because it's a long word. And so from there we can show that an MN sequence exists if and only if an NM sequence exists. So we can always swap the two. So we know that there's no 1-2 sequence. Now we know there's no 2-1 sequence. That's a logical consequence of the work we just showed. Suppose there was a 2-1 sequence. Well, we've just shown that a 1-2 sequence would have to exist. But we know 1-2 sequences can't exist. That was the B part of this question. So that means our original assumption of 2-1 sequence existing had to be false. So there's no 2-1 sequence. Now the other theory-based question we had, and this is the one I think will probably go somewhere, because we can talk about greatest common divisors. So as always, to show that if we have a sequence, we get another type of sequence, we have to actually define this sequence from the x1, x2, the given sequence. So we're going to say that yi is equal to xri. Okay? So every nth thing becomes every nth x position becomes our y position. We need to show that this is Mn. So we can pretty clearly see that if xi is A, that means that xri is A. And since it's an Rm-Rn sequence, Rm spaces after that Ri will have to be a B. But the way our sequence of y's is defined, that tells us exactly what yi plus m is. It's got to be a B. Now, if yi was a B, n steps later we should have an A. Well, xri will also have to be a B. So combining this with part C, an Mn sequence exists if and only if an Rm-Rn sequence exists for any positive value R. Okay, so that tells me I can just assume that M and N have a greatest common divisor of 1. Why GCD equal to 1? Because otherwise we would just need to show a much simpler sequence exists by our previous work. So we can assume that M and N have greatest common divisor of 1, or they're relatively prime is another term for that. Okay, so that's reduced our workload a whole lot, but we still do not have a plan of attack for how to show which M's and N's do exist. We know 1, 1 exists, sure. How about 1, 2? Well, 1, 2 can't exist. And in lieu of another way of doing this, I think we should just check, see if we can find a pattern with these guys. I mean, there's probably a reason they gave us the 1, 2 not existing. We'll try some of these and see if we can find a pattern. 1, 3 it doesn't reduce to a previous case. Definitely going to have the greatest common divisor of 1. Okay, so suppose it starts with an A. Well, then right after that we have to have a B, and then 3 spaces later we have to have an A, and right after that there's a B. 3 spaces later, an A, B. So what could we fill in here? Well, we could try an A, and then right after that we'd have to have a B, and then 2 spaces later an A, and then B and an A. So this all works out. So a 1, 3 exists. How about a 1, 4? Okay, A, B, blank, 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 A, B, blank, 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 A, B. Alright, so that's a lot of blanks to fill in, but that's okay. How about we try an A here? A, B, blank, 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 A, B, blank, blank, blank. Alright, we're looking good. Now, how about an A here? A, B, that does not work. Well, how about a B? B, blank, 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 A, well, that also doesn't work. Okay, well, maybe we shouldn't have an A here. Maybe we should have a B. But I think many of you will probably see that it doesn't really matter what we do. 1, 4 is not going to work. Blank, blank, blank. Should have an A here. That doesn't work either. See, where it does work, it falls pretty quickly into place. We've never had to go hunting for a specific case where the 1, 3 exists. It just sort of fell into our lap by choosing things. Now, I admit I haven't exhausted all possible cases, so there could be a 1, 4, but it doesn't look like it'll exist. How about a 1, 5? I think A, B, A, B, A, B will work as well. 1, 6, I'm pretty sure that will not work. A, B, blank, 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 blank. So 1, 2, 3, 4, 5, 6. I can't have an A here, so I'd have to have a B here. Because if I have an A here, this guy's got to be a B. So he's got to be a B. What else can I do? Suppose there's an A here. That'll give me a B. That's fine. How about this guy? If he can be an A, can he be a B? I want to sort of get a contradiction somewhere. Like here, it was pretty clear that this one wouldn't work. So let's try an A, B here. And that'll work out fine. We'll be left with an A and a B here. How about an A, B? That'll be fine. So that this one's a B. Further down the line, I'm pretty sure it's A, B, A, B, A, B. So that should be an A. So it looks like odd and odd are fine, odd and even, and that's a no-no. And we don't need to test even because then they have a common divisor of 1. Or they don't have a common divisor of 1. Now, admittedly, all it looks like is 1 odd and 1 even. Don't worry, but we can generalize. If we're wrong, we'll come back and take a look. But it's the final question. We're likely running out of time. So we just sort of jump to conclusions a little bit. We have our hypothesis. It's general enough to solve the question. We would just need to prove it. So it looks like odd exists. Odd even does not exist. Okay? Odd, we should be able to show that. AB should work. So xi is A if I odd, B if I even. Okay, well, let's check. If xi is A, then I is odd. And so since n is odd, and this is an even index, we get a B. How about if xi is B? Then we know that I is even. Write that a little clearer. So we get an A. So we get an MN sequence. For both of these guys being odd. Okay. So we definitely showed that 3-5 sequence exists and a 7-101 sequence exists. Now the harder part, can we show that odd-even does not exist? Okay? So here we're going to have to suppose a sequence does exist and find a place where two indices are telling us that the same place should be both an A and a B, which is a contradiction. So now let's suppose M is odd and is even. We suppose we have a sequence. Then we try and break it and show that it contradicts its own rules, so it can't exist. Alright, well, that's a good question. What would we need to do? Well, let's take a look. If some index has got to be an A, because if you have a B somewhere, eventually later you're going to have an A. So this value here is odd. So we can find A at both even and odd positions in our sequence. Notice this is different than AB, 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 where A had to only be in the odd positions and B was only in the even positions. So this is likely going to form the basis of somehow contradicting us. Okay, so I plus M is B. What about I plus N? Alright, so if I plus N is an A, so if we just add M to this, M spaces after an A, we should get a B. So that can't happen, so I plus N will always have to be a B. So if I have xi as an A, M spaces before it, I can't have an A, otherwise xi should be a B, which it's not. So M spaces before it, I have to have a B. Right, I'm just fiddling around with the sequence. Right now, I have no exact ideas how I'm going to show this doesn't exist. But showing that more things have to be A's or B's will likely lead me somewhere to a contradiction. So if I have a B, N spaces before that, I have to have an A. Because if it were a B, then N spaces after which is xi, that would need to be an A. That contradicts our knowledge that it's a B. Okay, we have a flaw. We have an impasse that we cannot go around. I mean, that's what impasse means, so. All right. So if I know what xi is, I know what xi plus m is, I know what xi minus m is. And I can, if I have a b, which I do, I can add n to that. So I get an A here, which is great. So I'm starting to get linear combinations of M and N. Okay? Now, I should be able to get linear combination, because the greatest common divisor of M and N has to be 1, I should be able to get a linear combination of them that exactly expresses the value of 1. And then I'd know what xi plus 1 is, maybe. Okay. What are we trying to get at? I do apologize for the dead air. I'm trying to think. It's a tricky question. I think we're almost there. If we can show this, then we have the question all sewn up. So all the work we've done beforehand would easily be worth the bulk of the marks on this question. We just have this last little bit to figure out. Why can't we get m and n being odd and even? Well, let's take a look at some of our previous ones that didn't work out. So here we went A, B, but then when we tried to put an A in here, this one didn't work. And we tried to put a B in here, this one didn't work. But that was still fine there. So what spot was that failed? So can I get any arbitrary linear combination? I am inclined to think no, because we can only go, if we have an A, we can go back 1 M, but we can't go back 2 M's. Or can we? So if xi is an A, and x minus m is a B, what about x minus 2m? Well, if it's an A, then that makes sense, but if it's a B, there's no problem with that. You see? It should be an A, I think, but there's no issue with it being a B. Exactly. Nothing that I can see right off the top of my head. So let's see, xi equals 2m, and I want it 2m, I minus 2m. I want it to be an A. What if it's a B? Then xi minus 2m plus n is an A. Okay. And then m spaces after that, I'll get I minus m plus A is a B. So that fellow's a B. Now, is there a contradiction with anything else I've figured out already? Minus m plus n. Well, I think I just... Yeah, that doesn't work. That's a contradiction, right? I minus m plus n is an A here, because I minus m is a B, so we add on m, we're all set. 2m, if we go back 2m, it can't be a B, because then N later, it's got to be an A, and then M after that, it'd have to be a B. So any linear combination, we know M and N have greatest common divisor of 1. So a linear combination of two of those guys is eventually going to be 1. So for arbitrary integers here, C and D, what might M and N be? So when we get, so what do we have? We have 0, 0, we get an A. If we have 1, 0, we have to have a B. Okay, up here, if we have negative 2, 0, we have to have an A. And negative 1, 0, we have to have a B. I think we just figured out a second ago after n spaces after an A, we have to have a B. So 2 spaces after that, we have to have an A. So it looks like if the sum of C and D is even, we'll get an A. If it's odd, we get a B. Negative 1 and 1 gets us an A. Negative 1 gets us an A. Negative 1, and so negative 1, 0 would be a B, and negative 1, 1 would be an A. So I think if C plus D is even, then we get an A. If C plus D is odd, then we get a B. Okay, now the question is, how the heck do we prove that? Alright, so we know that M spaces before a B will have to have an A. So n spaces after an A, we have a B. I believe we showed that. N spaces after A, we have a B. Well, M spaces after an A, we have a B as well. So by symmetry, M spaces after an A, we have a B. So M spaces after a B, we have an A. And likewise before. Okay. Now it's not even mattering what D is. We know that if we go, N before an A, we'll have a B, and then N before that, we'll have an A, and so on. So it's really mattering how many N's we go back, an even number or an odd number. Now, all this came from the work we sort of just did. All right, so in an MN sequence with M odd and N even, we now know that if we are handed an A, we can tell you exactly what came before it in terms of linear combinations of M and N, and exactly what comes after it in terms of M and N. linear combinations of m and n. Okay. Now we know the greatest common divisor of m and n is 1. So we can find a linear combination of these two that gives us 1. They're integers a and b. So using this sort of stuff, we can figure out exactly what came before m and exactly the thing right after an a and right before an a. Let's not jump the gun a bit. A must be odd. Otherwise, our sum is divisible by 2. M is odd. So if A is even, we get an even number here, and N is even, so we definitely get an even number here. Even plus an even is equal to 1? I don't think so. So we know A is definitely going to be odd. Can we show something like B has to be even? Let's see here. Right, we can add and subtract mn at will, and that means we can change a and b. The a and b up here that make a linear combination of 1 are not unique. So we can assume b is odd, or we can assume b is even. We know a is odd. So we can use one linear combination where b is odd, where b is even, and then a plus b is even, to tell us that this should be a b. And we can find a double prime, b double prime, still integers. All we've done is sort of shift a up by an even number, so it's still odd. But we shifted b down by an odd number, so b has shifted from even to odd. And we can find a double prime, b double prime, even. So x plus 1, the one right after the a, well, he's any old linear combination. But this time, being a double prime plus b double prime being even tells us that the number right after a would have to be a. Whereas up here, we showed that the number right after a would have to be b. Contradiction. Okay, that took us way too long. I don't even want to see the time on this video. There's definitely room for improvement. I should have noticed that linear combination thing a little quicker. We're not done the question yet, but we're close. We can sort of sum up. So we can find an MN sequence if and only if, when you divide them by their greatest common divisor, they both are odd numbers. Another way we could write this, had some time to think about this in the back of my mind while I was working on that stupid odd-even problem. If we write them in terms of powers of 2, and by no means are you supposed to jump from this to this. I've been working along I've been trying to think of a nice way to write all these out rather than just making it conditional in the GCD. So a nicer way we can say this, an MN sequence exists if and only if A equals C. Why? Well, suppose A was bigger than C. 2C and then some other bits will be the greatest common divisor. M divided by 2C and whatever other little bits will be even, whereas N divided by 2C and some other odd number that makes up the greatest common divisor, that'll be odd. We'll have an even and odd case. So if you wanted to, you could explain that a little more, but frankly, I think I've spent way too much time on this problem. It took a while to realize the linear combination thing at the end, but it has been a lengthy question. But thank you all for your patience. Let's just double check the contest. There's nothing else we need to do. Determine all pairs MN for which there is an MN sequence. Okay, great. We have our greatest common divisor condition. We eventually found that. That reduced it to evens and odds, because an even case, greatest common divisor is not 1. And so that gave us the condition at the end, and I just sort of cleaned it up for fun. But I think either condition that I stated on the last page would work just fine. So it's been a heck of a contest, and quite a lengthy question number 3. But thanks for sticking it out, those who did. If you didn't, that's okay. I imagine a couple people said, he's taking way too long, I'm just going to read the solutions that Waterloo provides, which is a perfectly fine way of doing things. But it's nice, I've always found when I was growing up, it's nice to see that the people who seem to know what they're doing with these contests can still screw up or take a long time. They don't just instantly know the answers. And I think if there was virtue to seeing that, I've definitely demonstrated it today. But thank you all so much for watching, and I'll see you guys in another contest or another math video at some point. So thank you all so much for watching. It's been fun.